this music I'm making, what the heck is it? And he says, oh, it's experimental electronic.
There you go, there you go. He also facilitates a Strange book club, a study group dedicated to exploring the influential Alan Strange text, electronic music systems, controls, and techniques. My kind of guy here. The second edition of which recently enjoyed a reprint through the efforts of Dr. Jason Nolan at the Representative Ecological Lab of the Toronto Metropolitan University. So please give a warm welcome to Steve.
Thanks so much, Anthony and Ross, for inviting me here. It's a pleasure to talk to you about synthesizers, probably one of my favorite topics. I'm going to start out by saying I am not an engineer of any description myself. I will occasionally edge into the periphery of my understanding of some concepts to do with formulas and math and fast Fourier transforms. If my language gets a little vague, I apologize in advance. But hopefully Tristan and Jeff can fill in some of the details once I'm finished. I'm going to start around 1960. And there were certainly a lot of electric and electronic instruments around by then. But some interesting things happened, and it's kind of a watershed year. Pierre Schaeffer, who's a composer and educator in France, had introduced this idea of musique concrète. And it was very popular in the academic music studios at that time, starting in the late 1940s, I think, and it involved holding a microphone up to anything that made noise and putting it on tape and cutting it up and manipulating it and using that as a compositional medium. And what happened in 1960 is a gentleman named Harold Bode, who some of you might be familiar with, who had worked with the Hohner Organ Company in Germany and now is with the Este Organ Company in the States, presented a new concept to the AES in New York. And that was, rather than going into a studio and assembling a collection of disparate equipment to create electronic music, like oscillators that had one big knob to change the pitch of and that sort of thing, but the idea was to create a system of compatible components or modules which were purpose-built to interact with each other, and this system included a voltage-controlled amplifier, significantly, and favored transistors over tubes, which was kind of a new thing in the 60s, and here he is with one of his inventions around that time. Not to lessen the impact of any of the guys I'm going to mention in the next few minutes, this guy is really kind of one of the unsung heroes of electronic music, and I consider him to be the father of the modular synthesizer. So Bode published those ideas in a magazine article in 1961, and that article caught the interest of a young Robert Moog, who's pictured here in 1970. Moog had been building and selling theremins with his dad and had done a bit of contract work for the musician and inventor and composer Raymond Scott. But the theremin business wasn't really a growth industry, as you can imagine, and Moog was looking for other things to do, and he started applying the concept of voltage control to his existing circuits and to create what would eventually become the Moog synthesizer. He was, by all accounts, a very collaborative and open guy. He sought input from composers, engineers, and academics. And at the suggestion of one of his colleagues, musician Herb Deutsch, he visited the University of Toronto Electronic Music Studio in 1964. And they received his presentation quite warmly, and the composer Gustav Chiamaga suggested what would really add to the presentation, or to his instrument, was if he could add voltage control to something like the filters that they were using in the studio at the time. And that became the concept of the first voltage-controlled filter, commissioned by UTEMS in 1964. And the Moog synthesizer made its debut at the AES in New York in that year. While all this had been going on, around the same time in California, composers Morton Subotnick and Raymond Sender of Mills College, and later the San Francisco Music Center. You see the tie into music concrete there. It was all over the Western music scene, as it was called at the time. They commissioned engineer and musician Don Buchla to create an electronic instrument for live performance. Now, the intent of this instrument was to create sounds that had never been heard before, and while it shared some of the basic components of Moog's instrument and was a modular analog synthesizer, it would produce sound through significantly different means. The Buchla 100 did not have a traditional keyboard, and rather than filtering, relied on wave shaping, wave folding, audio rate modulation, and incorporated random voltage generators and voltage sequences as control sources. In 1967, the first piece of electronic music commissioned by a record company was released on vinyl, Morton Subotnick's Silver Apples of the Moon, which was performed on the Buchla 100. And Wendy Carlos released Switched On Bach, performed on the Moog synthesizer the following year. It would go on to sell over 1 million copies by 1974, win multiple Grammy Awards, and spawn numerous Switched On imitators. And if you're of my generation, your parents likely had a copy of it in their record collection. I might be able to play here's what the Subotnick sounds like. Didn't expect to have sound. And of course, I'm sure you know this one. While analog synthesis was taking hold in electronic music studios and performance halls throughout the 60s, advancements in computer technology were making it possible to explore the potential of synthesis in the digital realm. In 1964, this is the same year the Moog synthesizer was introduced, J.W. Cooley and John Tukey rediscovered an algorithm that had originally been invented by Carl Friedrich Gauss in 1805, the fast Fourier transform. This algorithm would become indispensable in the development of computer-based samplers and digital signal processing in coming decades, allowing us to analyze and deconstruct sounds into their constituent harmonics. This is the part that I know absolutely nothing about. And in 1967, John Chowning was working on some theories on the localization of sound at the Stanford AI lab in California using Bell computer equipment. He discovered that by modulating sine waves at audio rates at intervals defined by precise mathematical ratios, you could create rich new timbres. It would be 6 years before Stanford found a development partner in Yamaha, and the first commercially available FM synthesizers would not start to appear until the next decade. And that's always been a fascinating thing to me. While people were hands-on creating instruments with through-hole components, the seeds were being sown of these extremely powerful digital instruments that wouldn't even be feasible for at least a decade or so. So as I'm sure you all know, the Mini Moog was introduced in 1970 as a compact, affordable performance instrument with hardwired signal path, oscillator to filter to amplifier. It was very limited compared to the modular synthesizer that preceded it, but it was capable of producing a wide variety of sounds and is still a common sight on stages and studios over 50 years later. I was at a Squeeze concert at Massey Hall a couple weeks ago, and there was an original Model D on the stage, perfect working order and sounding great, of course. As early as 1970, modular and semi-modular synthesizers were being produced by a handful of companies in Europe and the US. In 1972, Alan Strange published the first edition of Electronic Music Systems, Techniques, and Controls, which would become a definitive text on composition and performance using electronic instruments. And he'd go on to write the manual for some of Don Buchla's instruments. And then in the 70s, the market exploded, with manufacturers from all over the world, old and new, producing instruments. The integrated non-modular keyboard module dominated, although new modular and semi-modular instruments were introduced throughout the decade. Just a few examples of our favorites here. They became staples of virtually every popular music form of the time and spawned a few of their own. And then, before the end of the decade, developments in microprocessor technology ushered in an era of polyphonic keyboards with patch storage and digitally controlled oscillators that solved some of the tuning issues common in their predecessors. Advances in digital technology were also making a new type of instrument possible. The New England Digital Synclavier had a starting price of $25,000 in 1979, up to $200,000 with options, and offered FM synthesis, additive synthesis, sampling, and resynthesis, and that is the ability to sample a sound, analyze it, and then manipulate its harmonics to create new, never-heard-before sounds. The Fairlight computer music instrument was a complete music workstation, offered 16-bit sampling, Fourier transforms, graphic waveform drawing and editing, and an 80-track polyphonic sequencer. Additive synthesis was also manifested around this time in the Kumar General Development System. And its pared down sibling, the Synergy Digital Synthesizer. These instruments allowed you to construct sounds from a series of harmonics and also had some FM functionality. Additive synthesis, if you're not familiar with it, the Hammond organ and the organs that preceded it are kind of in the same family. In the digital realm, I have attempted it and found it to be a bit like trying to build a sandcastle with tweezers. But it has some proponents, notably Wendy Carlos at the time, but these instruments only remained in production for a few years, and only about 700 of the Synergy keyboards were produced, and the next slide will explain why. 1983, the Yamaha DX7 was introduced, putting FM synthesis into the hands of working musicians for around $2,000, becoming the best-selling keyboard in history, selling over 200,000 units before the end of the decade. By comparison, the first run of Minimo's about 12,000. They're complicated to program. Most users relied only on presets, but they offered a new type of sound that was clean and responsive. The 1980s saw a dramatic shift in the synthesizer market. Analog synthesizers fell out of favor, and VCOs were replaced with wavetables that could hold digital versions of analog waveforms and much more. Samplers became affordable eventually and made new genres of music possible, particularly in the case of Roger Lynn's MPC-60, pictured in the center there. The familiar knobs of the previous decade synthesizers seemed on the verge of extinction. Samplers begat romplers, which played back samples from ROM. Romplers begat workstations, which included multi-track sequencers and effects. But it was becoming clear that many musicians felt analog synthesis had been left behind too hastily. Thankfully, virtual analog technology was getting pretty good at imitating it. The Nord Lead, one of the first true virtual analog synthesizers, appeared in 1994. The 90s also saw the introduction of physical modeling synthesis, the concept of recreating resonant properties of a physical object through mathematical equations, and this had been around since the 70s. The Carplus-Strong algorithm, which dealt primarily with plucked strings, had been published in 1981. The Yamaha VL1 and Korg Prophecy pictured here were early examples of synthesizers that used these principles. Modular synthesis had never gone away, though, but it had become a bit of a rarefied pursuit. A few manufacturers had been operating continuously since the 70s when Dieter Doepfer introduced the A100 system in 1995, based on the existing Eurocard format. The current tally of Eurorack module designs uploaded to the database on Modular Grid is in excess of 15,000, and they cover the gamut of synthesis types and architectures. In 2000, Alesis released the Andromeda A6, a 16-voice analog synth. Moog Music would release the Mini Moog Voyager in 2002, and a new generation of analog synthesizers would follow. So I'll just quickly recap everything that happened in those past 30 years or so. Analog subtractive synthesis, the idea of taking a rich source and filtering out harmonics. West Coast synthesis, the Buchla type, favoring low-pass gates instead of resonant filters, wave shaping, wave folding, audio rate modulation. FM synthesis, which I'm told is more accurately referred to as phase modulation rather than frequency modulation. Again, I can only trust that that is accurate, but I can't tell you why. Additive synthesis, wavetable synthesis, sampling, resynthesis, and physical modeling. A couple techniques that bear mentioning. There's no governing body, of course, that decides what is a type of synthesis and what isn't. And I have opinions about these, but I'm willing to debate them. Vector synthesis always struck me as mixing sounds from 4 quadrants, and how you produce those sounds is a more significant question as to what kind of synthesis you're using. But you talk about vector synthesis, you know you're talking about a wave station or a profit VS. Granular synthesis, another process that's only available through the digital realm, chopping up sound into tiny bits, creating clouds, stretching them, repitching them. Speech formant synthesis, which is another 20-minute talk all its own. All I'll say about that is that it was actually the primary area that Ray Kurzweil was in before he got into designing samplers. In fact, he had created a text-to-speech device for Stevie Wonder. And Stevie Wonder said, hey, you can get a computer to read a page and sound like a human. Can you make an instrument that sounds like a piano? Kurzweil said, probably. And of course, vacuum tube and valve synths, the ones that were kind of set aside in the 60s. They have a sound all their own. You can get valve-based modular components and even complete polyphonic vacuum tube synthesizers if you have the patience and the bankroll. Again, because sometimes synthesizer manufacturers would just stamp a type of synthesis onto a keyboard or come up with a new name to avoid infringing on someone else's copyright. We have phase distortion, which is Casio's version of FM synthesis. Linear algorithmic synthesis, which is simply tacking a sampled transient onto a wavetable to get a little more mileage out of your limited memory. Wave sequencing, obviously the chord wave station. Transwave synthesis is Ansonic's name for wavetable synthesis. And vast variable architecture synthesis technology was the digital algorithmic system that Kurzweil came up with for the K2000. This is another very prescient statement from 1963. Max Matthews was a composer and educator. There are no theoretical limits to the performance of the computer as a source of musical sounds. That is absolutely where we are right now. Every form of synthesis I've just described is now available in software format. Modular manufacturers have licensed virtual versions of many of their products so they can be used in the box as sound sources or processors. That's a VCD rack up in the top right. And this is a two-way street, of course. Microprocessors are now fast and inexpensive enough for musicians to create and experiment with their own software-based modules in the modular environment. This is the Electrosmith Daisy device with built-in processor. And modular synthesizers are a common sight on stages once again. Analog synthesizers share shelf space with at music stores with the latest hybrid digital workstations. This is a rare good news story. I like to tell people it's really a golden age of synthesis. Virtually any type of audio synthesis that has been devised is now available to people who want to make music, who want to create virtually any sound that has been imagined, and quite a few that have not yet. And as a final closing word, in 2023, Toronto Metropolitan University published a reprint of Alan Strange's electronic music text for the first time in over 40 years, following a Kickstarter launched by Dr. Jason Nolan that raised over $250,000 in about 2 months. So thanks for listening to my long-winded talk. If you want to get together and chat about any of these subjects, I'd be happy to get into whatever details I know. But thanks so much for your time.
Thanks, Steve. Well, Tristan, our next presenter, is getting ready to go. Does anybody have any immediate questions about history, or are there any other history buffs, synth buffs that have any questions or anything they want to add to that? Any trivia?
In the front?
Yes.
Is this book reprint for sale?
Yes, it is. I have a physical copy of it here somewhere. My copy's not for sale. It looks like this. It is available from online retailers. I believe Jason is working on a reprint right now, so I don't know if he has any copies in stock at Toronto Met, but yeah, if you want to see me afterwards, I'll definitely hook you up with some addresses and online
It is
stores.
available online, like, so Perfect Circuit in the US, they have it, Schneider's Light in Europe has it, and Moog Audio.
Oh, okay,
not sure
fantastic.
all. I have a feeling they might have copies, yeah.
Nightlife has it.
Oh, yeah, there you go, yeah.
So what makes this book so seminal in terms of like the history of, like, is it just influential to all the designers that came after it? Like, what makes it such a good resource for people to have in their collection?
It was originally designed as, it's basically an undergrad level text for people who were studying electronic music at universities using primarily analog instruments. Now, a lot of things you could do with these modular synthesizers are far out of the realm of what you could do even with a mini mode. But because of the explosion of interest in modular synthesizers and people delving into sound creation with repatching and cross-modulating these kind of instruments, people started seeking out this book, but it hadn't been published since the 80s. You could find really terrible PDFs of it, but it's really, even if you just bought a modular system and are just starting out and have no idea, you can get a copy of this book and start working through it, and it's a great introduction to all the processes, and has examples and history, and even some scores that were created for electronic musical instruments in the 70s. So it's a fascinating book.
So you said a lot of, well, Tristan, I can talk like,
Please
I can talk like this for days. So synthesizers really was like you said, it was very academia heavy. Like universities could afford them. In the picture for the ad for this event, it was okay. Here's trivia. Who knows what the synthesizer for the event notification? Who knows the synthesizer that was on the website? Does anybody know which synth that was?
2500?
No. It was a British company.
Synthi 100.
It was a Synthi 100. Does anybody know anybody like tell us about the Synthi 100? Why is that thing like? Because it was like an academic thing. How did academia breed people and encourage people to study electronic music?
Well, there were kind of two camps. The Buchla type, the Morton Subotnick sort of avant-garde composers who were following in the trend of music concrete and Karl-Heinz Stockhausen and that sort of thing, interested in getting away from tonality, not interested in imitating other sounds. Essentially, the polar opposite of the switched-on Bach approach. This was considered as worthy of study at a university, whereas popular music wasn't so much. The other thing is these instruments were extremely expensive.
Crazy expensive.
And in a lot of cases, the only people who could afford them were independently wealthy or institutions like universities. So instruments like the Synthi or the 2500, the ARP 2500, which many of you would know of as the Close Encounters synth, and certainly Buchla's larger things. You could only find them in university music studios.
Yeah.
But if you wanted to learn about synthesis and you had an interest,
Yeah, it was
get
a course.
Yeah, you could get a degree in making weird sounds.
Does anybody have a degree in weird sounds here? Just a second.
No, but
Jeff.
I mean, the first one was at Columbia Princeton. That was the first electronic music studio in the university in North America. The second one was here. You're right. It was here. They also had one at McGill when I was there, where we had a lot of stuff that came from the National Research Council.
Okay.
That was custom built and came from the National Research Council. Now, a lot of the stuff before that came out of bell labs, stuff like that. So there's a lineage here from like audio research and hardcore sort of industrial and sort of research into things that led to those before they got to the stage where modular synths were available and stuff like that. And the early digital research was all out of bell labs, right? Because it was all about telephony. They were all trying to kind of get the data down the line.
Right. Yeah.
Keep it intact and stuff like that. The academics got a hold of it and said, hey, what happens if you multiply it by, Kool-Aid?
Why would he?
And see what comes up. But it was actually pretty hardcore, like military research and space research and stuff like that. That read also the like time delayed spectrometry, which is an offshoot of 4D transform stuff, straight out of NASA.
Yeah.
You know, and like all the hi-fi stuff. It's kind of amazing that lineage, the kind of hardcore industrial lineage, is actually where stuff started to a large extent.
Yeah, and to his credit, John Chowning was a classically trained musician who got interested in this stuff and realized, in spite of not being mathematically inclined, he would have to go out and get a math degree to figure out how to realize the sounds that he was discovering. This gentleman in the white sweater, you had a question?
Yeah, I was actually just wondering how you guys did this, like in your own upbringing, like what led you to study this?
Well, I'm the youngest of 4 children. My eldest brother is about 7 years older than I am, and I was born in 1968. So I was taking piano lessons, and my eldest brother had discovered all these synthploitation, switched on everything, and he was into Kraftwerk and Emerson, Lake and Palmer, and I just kind of grew up in this stew of sounds. And so it wasn't long before I was kind of saving up from the paper route to rent to own a Korg monopoly from Long and McQuaid, and it was kind of a last minute decision. I was thinking of going into I think a math program at Waterloo, and at the very last minute, like to the shock of my parents, I said, no, I think I want to study electronic music instead, and they said,
For the money.
yeah, exactly, for the fame. Jeff.
This is also Jeff. Are you also Jeff? Did I hear Jeff?
I am too.
Yeah.
I already
This Jeff, you mentioned on Jeff. This Jeff, you mentioned National Research Council,
Yeah.
and Steve or anyone else in the room. When I thought of Hugh Kane and the electronic sack button, which you mentioned. But that's not something I know a lot of. Like I know there's a little mini documentary about him or something. Do you know anything about Hugh Kane's legacy in the National Research Council? I know David Sutherland talks about this a lot. Right?
There was around the time of the Fairlight, there was an instrument being built in Toronto, right?
I couldn't tell you.
It was Paul Hoffert and
Was it the McClavier?
What?
Was it the McClavier?
The McClavier, that's right.
Yeah, there was a dead one up at York when I was studying there in the late '80s.
That was built here. That was sometime. I know the guy. I know Paul. I should ask him.
I love there's a great quote, which is, if you want to solve a problem in the audio industry, the telephone industry has already solved it. So I imagine like all of these trickle down economics of the research is, the synthesizer and the musicians benefit from it. Same thing with recording studios. They benefited from the broadcasters getting rid of their audio equipments, et cetera, et cetera. So it's very much very much that type of thing. Well, it looks like Tristan almost might be ready. Yeah, almost.
See if the itchy might work.
We did not coordinate our outfits together, just for the record. It's just a fluke. But thank you, Steve.
Oh,
Let's give him a round of applause. Thanks very much. I introduce Tristan Miller from Catherine North Electronics. Let's get the audio check. And do you have audio coming off of this thing too? Anyway, 2 million knobs and twiddles, story of our life. So Tristan brought a little demonstration. It's going to be, I don't think it's a beeps and boops machine. It's more of a sawtooth, wave tooth kind of thing. But Tristan Miller began studying electronics at his youth and has been focused on various areas of audio systems. Tristan has spoken at the Audio Engineering Society previously on power systems, grounding, shielding. Talk about super nerd. my kind of guy. Controls, automation, acoustics, and synthesizers. Tristan is a studio owner as well as an electronics company owner that designs electronics to serve the broadcast, to serve the music industry. And he provides like international services for recording, live, broadcast, and the aerospace engine. So you know, it all kind of goes together. In his spare time, he's designing and fabricating. He has a fab shop in his own environment. I don't think he'll talk a little bit about that. But some of the stuff you will see here and maybe be able to touch during our little break is actually hand fabricated by him and his electronics team. Ladies and gentlemen, please welcome Tristan Miller.
There's a lot of knobs up here. I got just under 40 little slides to run through. I think I got 20 minutes or so. I guess about just under 30 seconds a slide. 25. Oh, I can slide off a little
They
bit.
just give away the minutes here.
All right, I'm just going to run through the simple parts that you can find in a modular synthesizer. I'm doing like a gloss over, where as an overview, we have a quick functional overview of building blocks of synthesizers. Things like oscillators, filters, amplifiers, envelopes, control voltage. What are they? How can these be manipulated and modified and modulate each other? And how can we patch them together to create something like a very simple monophonic instrument? I hope it works. There's a lot of knobs to put in here. So, what is an oscillator in the terms of like a modular synth? An oscillator, it can go left to right, left and right, up, down, positive to negative, hot and cold, yes and no, in and outs, whatever you want to reference there. An oscillator is a device that generates a repeating voltage waveform or a repeating waveform. The number of times that this generated waveform repeats within 1 second, that is what we call the frequency, which is a measurement of hertz. I hope that's kind of known knowledge. Anyways, alternating change of the value, it can be an instantaneous change. We have an oscillator that makes a square wave with a binary on or off. We can also have a pure tone, something with an infinite number of values over the time span, such as the curved rise and fall of a sine wave. Periodic waves with a gradual change can also exist, like the linear ramp of a triangle wave. Now, so periodic wave is just any wave that repeats within a kind of period of time. It's any pattern that cycles, such as the smooth changes that can also be combined with a sudden jump in a saw wave. As you can see, like the sudden drop down as the ramp then restarts. Patterns can also be naturally occurring and very complex within themselves. You can have the rhythmic beating of a heart. That is kind of an oscillation, maybe not consistent, but is a repeating pattern. And shapes can also be arbitrary, and sometimes they can appear to be made up. This is a little image that I drew in MS Paint. It is definitely made up, but you can have a waveform generator generate this pattern and repeat it consistently. Oh, I'm going to talk very fast, I'm sorry. So whatever pattern the oscillator is generating, it is basically repeating that waveform at what we call the fundamental frequency or the root frequency or the root note, because these frequencies can also be transferred to music realm. 440 being commonly tuned to an A, 440 hertz can also just be an oscillator at 440 hertz. All right, filters. Oh yeah, I'm sounding a little dry. I got time.
It's a perk.
Oh, trying to squeeze all this information into 20 minutes.
I get you. You're doing a good job.
All right, a filter, it is a building block of an equalizer. An equalizer, as we should know, it provides amplitude adjustments to a specific range of frequencies within a signal. You can boost bass, you can scoop out the mid-range, you can dial back the highs, and whatever other like mixing lingo you want to use to describe what you're EQing. Filters are easily lumped into some several categories based on the type of responses they have. You have low pass, high pass, band pass, notches, high shelves, low shelves, bell curves, and there's probably many more types of filters that are out there. Quick rundown is like a low pass, it reduces high frequencies and allows low frequencies to pass through. And a high pass, the opposite being it reduces the low frequencies, but it allows high frequencies to pass through. Band pass combines both of those, and we stop signals above and below the range that we want, and a band stop or a notch, it pulls out the frequencies within the range that we want to pull them out. Some important parameters of a filter include things like the cutoff frequency. That is the frequency where the filter actually begins to take effect. The slope of the EQ curve, or the filter curve, that is how steep the response is. Example would be like a 6 dB, 12, 24, 48 dB per octave reduction or increase. The quality factor, or the Q, is the width or the bandwidth of a filter's effective range. If you ever played with a parametric EQ, where you can actually see it on the screen as a plugin, you can make that bell very sharp or very soft and gentle, That's what we call the Q of the filter. Resonance typically has a little boost or a cut at the frequencies around that cutoff point. You hear like a frequency sweep of a filter, you hear that little whip sound that kind of happens. That's kind of the resonance giving you a little peak as that slides across your frequency range. And much like other audio processing equalizers, filters are used to control the frequency response of a complex waveform. It allows us to shape and manipulate a signal's tone or the timbre. What is an amplifier? Amplification is a change in signal strength. This can be voltage amplification, current amplification, or if you combine them, you have power amplification. This amount of change is known as gain. Gain is commonly measured as the ratio between the input and the output signals. Voltage, decibel gains are common ways to express such a ratio. Gain of 1,000 is 60 dB of gain, and so on. If your voltage gain is above 1 times, you will have an increase in signal strength. If the gain is exactly 1, you have no change, you have a unity gain. If you have a decimal point between 0 and 1 times gain, you actually decrease the signal strength. And if gain is negative at any point, you end up inverting the polarity of the output waveform. How does this all become a synth? Well, we patch things together. We plug things together, we tie them together, we hard solder it together, we connect things to each other. Such as an oscillator output can patch into the filter, a filter's output then goes into an amplifier, and then that amplifier patches into the speakers that we're all hearing. Very lovely. With this, we can now change the frequency of our oscillator. Turn the tuner on here. So we can fine tune where we're oscillating. We can then also sweep a frequency of the filter, and of course we can adjust the loudness, the amplitude of the signal itself. Everyone calm down, my greatest hits album is coming out next month. Relax. This simple path allows us, as I just said, we can generate a rich square wave at a set frequency. We can then filter out parts of the tone by changing the cutoff frequency of that filter, and then we can change the amplitude or the loudness of the amplifier. These little arrows are kind of pointing out exactly how I have these same modules patched in this little box. This is very fun to do, twisting knobs back and forth. We all love doing that with big mixing boards, but most of us that I know of don't have more than 2 hands. So manually controlling various adjustments and parameters very quickly becomes overwhelming. And the performance like this definitely relies entirely on the human interaction. If only there was a way to control these parameters, perhaps with some invisible force of magical energy that thrives from every living being, one that surrounds us and penetrates us and binds our galaxy together. It is not the force, it is this thing called control voltage. Control voltage is basically a signal that is used to remotely adjust a parameter of the device. Eurorack, the system being Eurorack, modular synthesizers, they operate on a positive and a negative 12-volt power supply, DC. Some cases they do have a dedicated 5-volt supply, specifically if a module needs high amounts of 5-volt power to feed it, big digital modules, etc. Not required, but the 12 plus and minus is the kind of the limitation of the power supply inside the module, inside the Eurorack. There's no other real specifications on signal ranges inside Eurorack, but there are common ranges that designers and signals do try to follow. Common one is a 10-volt peak-to-peak signal, but this can also be a unipolar waveform, or it can also be a bipolar waveform. Meaning, unipolar, this signal exists in one voltage polarity only. It can go from 0 to 12 volts, but it will never be negative. And you can also have a signal that's minus 12 up to 0 volts, but it will never be positive. That is a unipolar signal. Then we have bipolar, which can exist in both the positive and the negative ranges. It doesn't have to float around 0 point, it can hover up and down, but it has the potential and ability to go positive or negative. Audio signals, they are typically bipolar, and typically they do float around that 0 volt point. You may have a DC bias in like a waveform's pattern, or you can also deliberately add a bias. You can raise an oscillating waveform, if that's my 0, you can raise that waveform up. You can also center it, and you can raise it lower. You can bias and offset a waveform. Signals in Eurorack and other modular synths, they can easily be attenuated or amplified. This changes kind of the range that signal it kind of covers, or it also changes like what they were generated to do. You can just kind of scale things up or increase it. But being loosely aware of the signal that you have, that you're on your patch cable, that you're patching things in with, being aware of what signal this is, it allows you better choices on how to use that signal. but one of the greatest flexibilities of modular synthesizers is that any signal at any point can be an audio signal, or it can become a control voltage, or a control voltage can become an audio signal. There's no, yes, this is audio, it's just waves and signals that we're generating and connecting to each other. Voltage-controlled modules. Once we add voltage control to a module, we have a voltage-controlled module, such as the VCO, the voltage control filter, the VCF, the filter, and the VCA, the amplifier. In this demonstration modules, we can apply CV to control these following parameters. The oscillator, we can adjust the frequency, which is the pitch and the tuning of that oscillator. We have the ability to do a linear frequency modulation, a 1 volt per octave change, or an exponential frequency modulation. We have hard and soft sinks available, which kind of restart the waveform as it's generating. And we have pulse width modulation, and that, as a square wave, instead of being square, you can make that a pulse by changing the on and off time of the square wave. Filters, we can adjust the cutoff frequency, and this module we can adjust the Q or the resonance of the filter. And with an amplifier.
Question there. Go back up to the above there. So on those modules, I'm just noticing that like you have a jack and you have a knob. Could you maybe explain, like you say, well, VCF, I'm going to inject a voltage into it. Could you maybe explain how that jack and how that knob has a relationship on a module like that?
All right, this specific one, can I zoom in? This specific module, we have an audio in jack, which then goes to a potentiometer. That potentiometer, that knob, is just a volume control. It's an attenuator that the audio in jack goes straight into. This first FCV number 1, this has no attenuation. Whatever signal you plug into this jack will adjust the frequency completely. You have no control over how much signal affects where that frequency point is. A lot of modules add a second jack with an attenuator, so you can follow the little line here. Our FCV number 2 runs to this little pot. We have an attenuator. So I can give it a 10 volt signal. With that knob, I can turn that down to be 5 volts. The module will see 5 or 2 or 1 or 1.3. I can adjust the level of that signal that actually goes into the module itself. Q gives it a hard bias. This is generating control voltage inside the module, so I can modify the Q of the filter. And same with the frequency control for the Q. That runs down to another knob, which I can then attenuate that input signal, so I can kind of control how much that signal actually affects the Q of that.
So if a higher voltage goes into that FCQ, does it become sharper? Does it become wider? What is the effect of FCQ then?
That depends kind of entirely on the module itself and how it was designed. As I turn the bias here for the Q, you can hear kind of that howling that's happening. That's a spike in that Q. And as I reduce the voltage that's going to it, hard to hear it. Better if I had like the transfer curve on the screen, but you can hear like a flatter response. There's no peak that's happening. The rest of the jacks are just different outputs of this filter. This filter itself can give me a low pass, a high pass, a band pass, or a notch filter as an output. Similar thing with the VCA, I have control over CV number 2. That input jack here goes into the attenuator, and I can control how much my modulating signal actually affects the range of the amplifier itself. Where does all of this CV information come from? It can actually come from wherever you want it to. Control voltage can be anything. It can be coming from a keyboard, an envelope generator, other oscillators, sequencers, random noises, pattern generators, external signals, lights, sensors. You can even use a potato with electrodes. Weird people on YouTube, I don't know. I hope you're not in this room. Control signals can be performed by people with instruments. They can be generated by software and programming and performances, and they can also be self-generated by patching a wild number of modules together. And they can also just be measurements of naturally occurring values. You can have a seismic sensor and read over a long period of time, like earthquake activity, and you can use that to modulate some sort of pitch in a 3-hour-long drone performance of some sort. What you can do is basically endless. As let's just point out, there's over 15,000 modules that have been added to a database. I'm sure there's 15,000 more that are all do-it-yourself, homemade experiments. But the amount of modules and what they can do is almost endless. So where do we even start? Envelopes to create controlling shapes. An envelope is pretty much a type of a control signal. One of the more commonly found envelope generators is the ADSR generator, and variations of it. ADSR is your attack time, your decay time, your sustain time, your release time.
I don't mean to be a stickler, but could you label your axes and tell us what those are?
No. Yes. So horizontally, we're looking at time. We're looking at a signal and a waveform over time, and the signal strength, voltage level would be your vertical axis itself. That just gives you, as time goes by, you can have a slow ramp of an attack and a slow decay with a constant sustain and then a release. So this is a kind of a shape of something that we're able to generate over time. And with an envelope generator, typically we have control over all of these rise and fall times, although not always available. Other things that you have an envelope like this might also be an audio compressor. The side chain that detects the audio to tell it when to compress the signal. There's some sort of envelope generated to control that amplifier in the compressor to tell it to increase or decrease gain.
Is there a way you can manipulate the sort of trajectory of each of those lines? Like, can my attack sort of come at more of a circular angle, so it's not so harsh on each point?
Soon.
Okay.
All right, here's a little envelope generator patched into a bunch of modules. I'm going to trigger, because envelopes typically need to be told when to start. They can also self-oscillate when they're done. They can tell themselves to start again, but this is now set up to wait for my command. If I trigger it, and if it works, I'm generating an envelope. And you can hear this is now controlling the amplitude of the amplifier, the gain of the amplifier. You can hear the sound comes in and it comes out. But
Is
what
that
are we
greatest
actually
hits?
seeing? Handtech oscilloscopes, $95 on Amazon. They do the job. I'm going to send this one back. It's not the greatest. So bear with me. The triggering is a little wonky. Triggering is very wonky today. All right. This is now triggering itself. It's now repeating. It's easier to draw on the screen, but you can see I'm generating. Do we fully need to hear that entirely? We're generating this shape. This is controlling the amplitude of what you're hearing. I can change our attack time. And you can see immediately that initial slope here, it now ramps up, and you can hear the volume fade up and then follow the rest of the envelope, and vice versa. We can adjust the release time for a very long release, or we can just make this very fast. These don't have to be linear, as you asked. They don't have to be straight lines, so we can add any sort of generation or shape to it, and control how fast that envelope generates, changes its shape. And you're not stuck with just ADSR, you can have ADSR, DR, DR, DR. You can have many patterns. Basically, you're making this envelope that controls this level. If this works, sometimes, you're seeing, hopefully, our green waveform is what you're hearing, and you can see that yellow shape is following the amplitude of what you're hearing. That is the envelope that you're seeing that is controlling the amplifier. You can see the result of that is what the envelope's actually doing. It's changing the shape of the amplitude of this generated square wave. Similarly, we can also trigger a filter.
Just turn it down a little bit. What you're saying is way more important than what we're hearing.
Sorry, it's hard to tell how loud it is.
Yeah.
Eventually, you learn just like tune out these constant frequencies, especially running like a personal repair shop where it's like 1K all the time. Well, just to repeat what I just said, the amplitude of our output waveform now follows this envelope because that envelope is controlling the gain of this amplifier. We can also send an envelope to a filter. And that can also kind of be automated on its own. So that is how you can have an envelope controlling another module. You can also patch that into the oscillator. You can cause the pitch of the oscillator to go up and down. If you give that a constant shape like a triangle or another sine wave, you can modulate your pitch with a little bit of an up and down motion, which becomes kind of some kind of like vibrato. When the envelope signal controls the gain of an amplifier, we modulate the amplitude of the output. This is something called amplitude modulation. Same envelope can control the frequency of the oscillator, frequency modulation, and then we can use the same signal to open or close the filter. I'm sure there's a modulation term for that. I just didn't put it in the slide. But like oscillators, these envelopes are not limited to straight lines. They can be any sort of shape. And there's even things called like envelope followers, where a device can follow the amplitude of an external signal, and you can get that yellow shaped line that follows, say, my voice saying something. You get the pattern of the amplitude of a sample of some sort, or a real world sound. There's many ways to generate an envelope. The envelope is just there to control some parameter of another device. All right, MIDI to CV control, actually playing an instrument. MIDI, as we all know, it contains lots of digital information, and all of that can be converted to control voltage signals, which can then be used to control other components within a modular synthesizer. This example is going to use my little MIDI control voltage module, and I'm just going to generate signals from this little Axiom MIDI keyboard. I'm going to still have the envelope going into the amplifier and to the filter, but I'm going to be sending CV gate, or gate CV. This is a high and low signal, which measures high when any key on this keyboard is pressed. So a gate signal is, if you press any key, the gate is high, it's on, saying, hey, there's a key being pressed. Too many buttons.
I've been calling it M1D1.
There we go, there we go. So every time I hit a key, it's triggering my envelope, it is making that pattern to make the sound. The other signal I have going in here is the MIDI to pitch control voltage, and anytime you play a different note on this keyboard, the control voltage that's generated by my little MIDI module increases. The higher the note you play, the higher the voltage goes up, and typically you try to follow what we call the 1 volt per octave, where an increase of a control voltage of 1 volt represents a doubling of the frequency or an increase of the frequency to the next octave up. So with this, I can now change the pitch of the oscillator as well as trigger the amplifier to open up and allow sound to pass through with whatever shape I decide to create. From there, we can add even more fun stuff, such as the aftertouch. We can have a pitch bend wheel modulate other things. We can have other envelopes trigger. The amount of what you can patch and control is, as I said, almost endless. So what else can you do with a modular synthesizer other than square waves and beeps and boops? I haven't really gotten past the beeps and boops, but you can do whatever you want. There are thousands of different modules that are available, and this chat that I've rambled through really only scratches the surface on some of the bare, basic core components of a synthesizer. And we've also only just put together a single mono sound source here. You can double all of this and have 2 signals at the same time, or 3 signals, or 1,000 signals. You can increase this to whatever size you want this to be. There are things like drum machines, reverb units, ring modulation, phase, frequency followers, distortion effects, delay units, pitch shifting, samplers, mixers, multipliers, dividers, different filters, compression, expansion, vocoders, sequencers, sample and holds, bit modulation, and there's countless more devices that you can get. And all of those can easily be combined together in one little case, patched together, and you can generate one single control voltage from all that. And that single control voltage can go to another case and control one oscillator's pitch. You can do 1,000 devices to do one little thing, and it's endless. That's what I love about it. It's just so crazy of what you can do with modular synths. All right, now what you've all actually been waiting for is cats on synths.
So Tristan, thank you for that. That
was a lot.
was like start to finish, like that's a university course that they taught in the 60s in like 35 minutes. So a question about the modular synth stuff. Like, okay, so you said there were a couple standards in there. Voltage, that's like a standard, and then there's also 1 volt. Like, where did those volts? Like, why do we need that standard? This is it, leading into some. Why do we need standards like that to make these types of systems work?
Compatibility. Is that a good term?
Yeah,
for
yeah,
standards?
absolutely.
It's
Go,
just
go,
the
go.
compatibility is how does this keyboard know what frequency to tell this oscillator to play? They don't talk to each other. It's just the keyboard's like, 2.73 volts. And the oscillator's like, okay, I'm going to generate whatever I think that frequency is supposed to be. The compatibility, that 1 volt per octave, and you might be able to help me out a little bit of where that originated from, that goes maybe back to the Moog kind of era?
Yeah, Moog was 1 volt, Buchla was 1.2,
Yeah.
and then of course there's Hertz to octave systems.
And it's,
I have a friend who says the great thing about standards is that there are so many to choose from.
See, my thing about standards is nobody reads all of them before they create their own.
Yeah.
yeah. But it's the compatibility. It's having this device able to talk to something else and be relatively as close as it can be in tune with the other device. That 1 volt per octave, it's becoming very more popular, but as it is used, it's this oscillator can talk to a different keyboard that also has a 1 volt per octave out.
So you mentioned tuning. Okay, so like they're notoriously awful to tune, or like tuning is a relative term in music.
Well, that's the question that I have.
Go.
Like, I mean, so you have an octave, so you have a volt.
Yep.
And then an octave above it is 2 volts.
Yep.
And then every semitone is going to be 12th root of 2 above that, going upwards. If it's going to be in tempered.
Mm-hmm.
Right. So this is that standardized?
It's fun. Pretty much, yeah. We try to follow that scale of 12 notes within that kind of 1 volt range, which as I break it down, it works out to like what 0.08 volts, 0.83 or something.
It's 0.0595% if you want to look at that.
Well, through too.
I'm not mathing today.
Fractions are way more accurate than numbers.
But things like that make generating a signal hard because my little MIDI module is a little microcontroller. It's a teensy that's running that's doing pulse width modulation as that output to give me a DC voltage, and I can only be so accurate with the bits and the resolution, right? So that's where
That's the trick.
it's a little bit of issue, and that's where a little bit of tuning comes into play. So that's why fine-tuning the oscillator to that frequency is fun and important.
He does have a tuner hidden.
I don't know how to use it, but you know, it spins and it lights up,
Yeah,
changes
it's
colors.
complicated, and I appreciate it.
Okay, so in the black there, you've got a question.
I was gonna ask, like I'm working on a MIDI device, and I was thinking about like CD to MIDI or MIDI to CD. It's like there's there'd be a lot of loss in like resolution when you think of like a MIDI message itself in terms of like 0 to 127, but like in terms of like potential values you have for memory.
It really comes down to what is your analog to digital and your digital analog conversion, right?
Yeah.
Because if you have a high enough resolution, if you're doing 96 kilohertz sample rate on an input and you're able to do that at 24 bits, you can very accurately measure whatever CV you're putting into it. From there, you need a very accurate output to match the accuracy of that input.
Yeah.
So you can go down to 8 bits running, 8 kilohertz sample rate or something, and you're stuck in that resolution.
Yeah, like I was thinking like
You're talking about that, Jeff?
to CD, it's like let's say you want to tune an oscillator using MIDI message.
Yeah.
Our next talk, we'll talk about that in great detail. So this is like, there's an arc to this story too.
I'm doing the introductory class here. But you're right, there is that issue of the resolution, the accuracy, which also exists in just the recording world and the digital audio world of how fast of a sample rate and bit depth you want to use. CDs, if anyone remembers what those things are, 44, 1, 16-bit. No one in a studio records 16-bit audio anymore. You get laughed at. It's 24-bit or 32-bit floating. It's the resolution and the technology and the microcontrollers are so vastly improved that it's almost endless of what we can do.
Would you say that modular synth has kind of like democratized, like because of like the cheap microcontrollers, et cetera, has it made it more accessible to everyone?
Definitely more accessible, easier to manufacture. There's abundance of types of microcontrollers that have different features on the chips themselves, and also just the whole do-it-yourself, like the Arduino world, the Teensy world, the whole like home brewing controller world. It's massive. The hobbyist world has exploded because it's become so affordable and accessible that you're able to start picking away at your own little MIDI module. So it's so available that it has definitely exploded and made things accessible and available that we have over 15,000 registered modules.
I saw Art, you had a question, but you probably haven't answered.
You already answered.
Okay, okay.
That's what platform developer, you mentioned.
Some of them, both of these modules, my MIDI is a little teensy 4.0 and the envelope generator is a 4.1. Definitely overpowered for what I'm doing. You can go down to the Arduino stuff, the Amiga processors. I'm starting to play around with the ESP32s because they're about $4 for a little.
You're buying by the dozen now.
Dozen.
Oh yeah, man.
I buy a case of them.
Man, yeah, like electronics are cheaper by the thousand, let me tell you. Okay, folks, Tristan Miller, let's give him another round of applause. I brought a little something for today. So this is. So how many of you have heard this sound? Okay, right. So my wife, she got really upset with me one night. She says, "Why are you packaging these things at 3 o'clock in the morning?" And I found this.
What?
What?
No, you didn't.
So this is quiet packing tape. Seriously, is that not the coolest thing you've never seen before? I figured, like, what can I bring to an AES event that nobody's ever seen at an AES event? That to me, so I don't know.
Is it for packing in the middle of the night because you're leaving? Like, you don't want to wake anyone up?
Well, it was one of those things of like, you know, I do a lot of business on eBay. Who doesn't do a lot of business on eBay? Who doesn't have like 35 search filters on eBay for certain things? Like, I might be getting a notification right now for some strange, bizarro. Yeah, I got into machine, so I have a machine shop at home. So like tangential to audio, I realized that the hardest part of electronics building is the case it goes into. So who's ever heard that before? You know, like, you know what I'm talking about. So like anybody can build electronics, but not a lot of people can build the case in which things go into, and that's where a lot of designs kind of fall apart. So it's a very mechanical process, even though we don't talk about it that much. But that's how I met Jeff. And Jeff, I reached out to Jeff, and Jeff came into this, and Jeff is an experienced designer. And the mechanical side of electronics and engineering is something that is very important. But Jeff's not going to talk about that. He's going to talk about something else. And because Jeff runs Toronto-based manufacturer, it's called System 80. It was called Mini Systems before.
Mini System, just my old internet handle from 20 years ago.
There you go.
I still use it on my corporate Instagram.
The internet handles of yesteryear never disappear. You know, he has a special interest in bringing classic Japanese. Why just Japanese? Like
Just because of the history of house and techno and electro. That's it.
There you go. Analog designs to the Eurorack modular format. System 80 is known for its multi-mode filter module, the JOVE, as its Eurorack clone of the TR-808 drum machine. Jeff is an industry research partner at TMU Responsive Ecologies Lab, which you're going to have to explain a little bit about that. Ladies and gentlemen, please welcome Jeff Lee.
Thank you. Yeah, so today, I want to thank Steve and Tristan because I was just telling them before my talk that they perfectly set me up because now, if you didn't know already, you know all about the history of synthesis, the different synthesis methods, especially subtractive analog, which Steve talked about, and then Tristan went into detail. And so I'm going to get a bit more technical and talk about designing programmability into subtractive analog synthesizers. So all the synthesis methods that Steve talked about, the only one I'm going to talk about is the first one he talked about, which is what we call East Coast subtractive analog synthesis. I need to acknowledge my gracious host. So as Anthony said, I run a small Eurorack manufacturing company called System 80. I am hosted by the Responsive Ecologies Lab, which is a multidisciplinary research space at Toronto Metropolitan University. And they give me a couple of electronics workbenches and some space to work in. The lab is on Bay Street, so I like to say that I am the CEO of the Bay Street company. That's how I often introduce myself at parties. So I like synthesizers. This is my studio. About 15 years ago, I was into large format modular synthesis. So this is a different format than Eurorack, which was what we were talking about. This is what people call 5U. This is a sort of a copy of the old Moog synthesizers. This is actually one that was made in Toronto by a company called Vodcan, now sadly defunct. So this is where I made music with all these vintage synthesizers, and this was the state of it about 15 years ago. Then I had 4 children, and that was the end of my home music studio. That's kind of where I was really into making music, having a big analog studio, and then too many children, and then I packed up the studio and put it away, but I kept one foot in the synth world because I got interested in the technical side, which is sort of intimated by this last slide with a child who slept with my multimeter and actually threw a tantrum when I tried to take it away from him. So I got really interested. So when I was making music, my favorite synth was the Roland Jupiter 6. This is a analog polysynth from early 1980s, 82, something like that, 83. It's notable because along with the sequential circuits Prophet 600, it was the first commercial synth to have MIDI. They were released simultaneously or demonstrated simultaneously. And as you can see, it's a knob and switch laden, very hands-on interface, and it has an analog signal path. So it came out just a year or two before the DX7 and the whole mid to late 80s digital wave that ran all these analog polysynths. They went running and no one wanted to use them anymore. They turned up for low prices secondhand. So I love this synth. And the interesting thing about the synth is that if you're sort of a Roland synth nerd, is that all the Roland synths have, the vast majority of them have a similar filter, and they all kind of have, people have this Roland sound, they call it plasticky, and it's all over some of my favorite house and techno and electro records. But the Jupiter 6 has a different filter in it. It's a multi-mode filter, and it's kind of interesting. So once my children ran my synths out of the house, I got interested in the technical side, and I made a version of this filter, just breadboarded it and started working on it, and I turned it into a Eurorack module. So this is one of the modules that Tristan was talking about. It's a multi-mode filter. It works in the 3U Eurorack format, and this was very successful. This is what I used to launch my company, System 80. And it's how I met Anthony, because I needed panels made. So I went to Ward Beck, where Anthony used to work, and they had in-house metal shop, sadly no longer. And they made these amazing panels for me, and this was sort of the springboard to getting System 80 going. Then I did this crazy thing where I took an entire TR-808, which is the infamous Roland drum machine, and I compressed it into a 60U Eurorack module, just for fun. And then when I showed it to the world, people were like, I want that.
You said 60U.
Sorry, 60 HP, excuse me. Yeah.
So 60 HP, that's another standard. What the heck does HP mean? Like, what does that mean?
I know, I think of D&D and hit points.
Yeah, okay.
I actually can't remember, does anyone know what HP stands for? It refers to the width, right? U is the height.
Horizontal pitch?
Horizontal pitch, there you go. And 1 HP is 5.08 millimeters. That's, yeah, that's what I remember. So I've been really busy. I can't make enough of these. People want them for some reason. I don't really know why. I mean, I like it for myself, and so that's kind of primarily what we've been busy doing for the last 5 or 6 years, is making this drum machine. That's not what I'm going to talk about today, though. I'll just say this is what we do. We make Eurorack modules. We have a lineup of 6 or 7 modules now. Well, what I want to talk about today is my interest and obsession with designing programmability into subtractive analog synthesizers, and I'm going to talk about what that means. So yeah, I'm going to talk about what is programmability in an analog synth, why is it useful, and last thing I'm going to go into how is it achieved from a technical perspective. So thankfully Steve kind of already covered this. He talked about synthesizers in the early 60s being modular. So this is a Moog modular synthesizer. Individual units, they all need to be patched together, and they were analog. Importantly, voltage controlled, which is this concept that Tristan talked about, which I'm going to keep coming back to. They were modular, so you had separate oscillators, separate filters, separate VCAs, separate modulation sources like LFOs and envelope generators, and they were, for the most part, unless you had a really, really big system, they were monophonic. You could play only one note at a time. Then Steve already showed us a picture of this. This was the Mini Moog, which came out in the early 70s, and it was a fixed signal path. It was portable, so that made it popular with musicians. They could cart it around, bring it on tour. And it had a fixed signal path, which meant that you had sort of how an oscillator or filter or amplifier were modulated. That was predetermined behind the panel, and you just had all the knobs and switches to control that path. So this is what I would describe as the typical analog fixed signal path, which again I think Tristan touched on. This is sort of arrived, I think, over the years by consensus, that if you have an analog synthesizer, subtractive analog synthesizer, this is sort of what designers arrived at as like, this is a good sort of combination of units that you can put together to make a wide variety of sounds. So if you want to follow the Western 12-note scale, you have a keyboard that controls the pitch of 2 oscillators. Often there were a lot of synths that just had 1 oscillator. The kind of fancier ones had 2 oscillators. They go into a mixer, so the 2 signals are mixed together. They then go into a filter to roll off the harmonics and add resonance. And then they go into an amplifier. And typically the filter and the VCA were controlled by an envelope generator, ADSR, which Tristan demonstrated for us. And the other module we haven't talked about much is an LFO, but that's just a low frequency oscillator, so it has repeating patterns, but that run at below audio rate typically. And so this, each element, this is what we call the audio path, right? And then I show that's in the sort of orange, yellowy-orange color, and then we have the modulation path. And so you have the modulators, the keyboard, the LFO, and the ADSR, and then you have the audio path. So in this example, this is we have an analog audio path. Analog oscillators go into an analog mixer, go into an analog filter, go into an analog VCA, come out through your speaker. The important thing is that each element uses voltage control. Keep this in mind because this is kind of what I would call the archetypal synthesizer voice.
I have a question.
Yes.
And this is kind of random, but in this sort of setup, is it possible for the LFO to bypass the VCO2 and just affect the VCO1?
It can be. It depends on, if it's a synth voice, it depends on how you set it up. You can have a switch that switches between VCO1, VCO2, or both. That was often a common configuration. That signal path and these original monophonic analog synthesizers, they had some limits that musicians started to press synth designers about. They said, we want polyphony, we want to be able to play chords. And then the other interesting thing, which people sort of maybe don't think about much, is that you look at something like the Mini Moog, it's got, I don't know, 15 or 20 knobs on it, and every time you turn that knob, you change the sound. If you're a touring or working musician and you're on stage, you're dialing in different sounds for different songs. And so people thought, well, wouldn't it be a nice idea if you could just press a button and recall different sounds? And so I'm going to talk about, mostly I'm going to talk about patch memory and a little bit about polyphony. Really, I'm going to talk about both. So we're going to say, how are these features achieved? So this is taken from the service manual of the Roland Jupiter 4, which was one of the early polyphonic synthesizers. And as you can probably see, the trick to making a programmable polyphonic synthesizer is you have to add a computer. You throw a computer in, and it was only in the late 70s that microchips became sort of cheap and accessible enough that they could start turning up in like consumer electronic devices like a synthesizer. So in a conventional synthesizer, this was back, because you have to remember this is 1978, Right? A conventional synthesizer had a control panel which had a bunch of potentiometers and switches on it, and they directly controlled the elements in the synth circuits, the VCO, the VCF, and the VCA. In order to achieve polyphony and programmability, you have to separate and abstract the control panel from the synth circuit, and you do that by putting a computer in it. And I'm going to go into more detail about what this part of all this means. So here's another example from, I think, the Sequential Circuits Prophet 5 service manual. Here's your keyboard and your control panel. So here's your black and white piano keys, and then you have all of your knobs and switches on the control panel. That sends information to the computer system. The computer system then sends out a bunch of voltages, and depending on how you play the keys, you have to multiply your synth voice, that archetypal synth voice that I showed earlier. If you want to have 6 voices, then you need to have 6 of those synthesizer circuits in your synth, and then they get mixed together to create your audio out. So to drive the point home, imagine this is a synthesizer with a control panel and a keyboard. Instead of these knobs directly controlling the synth circuits, they go through your computer, and you have, if this is a 5-voice synthesizer, you have 5 little mini synthesizers inside your polyphonic synthesizer. So you have your potentiometers, and this is the kind of concept I wanted to introduce. How do you do that? What is this middle section here, right? And that's done through the potentiometers are read by analog to digital converters, which are then, so the potentiometer information is converted to digital information. That's interpreted by the CPU. That's then used to generate analog control voltages through a digital to analog converter, and then those go to your synth voices. So I'm going to explain that in more detail. This is the block diagram of the first fully programmable polyphonic synthesizer. It was the Sequential Circuits Prophet 5. And as you can see, back in the day, you had the CPU had separate RAM, separate programmable memory, and then you had a whole bunch of, in fact, these things were weird because they had a digital to analog converter, but then it was repurposed as an analog to digital converter in a way that maybe some of you know about. So it gets very complex very fast when you want to create, in the analog realm, you want to add digital control to all of these analog circuits. So this was the sort of state of the art in 1979. So why am I so interested in these things? So these are analog polyphonic synthesizers. There was a slew of really high-end, expensive ones that came out in the late 70s and early 80s. There's the Memory Moog, the Roland Jupiter 8, the Yamaha CS80, the very first one, the Sequential Circuits Prophet 5, the Oberheim OBX. These things got left in the dust after the digital revolution of the DX7, but there's been a resurgence, and my question is why? There's something about these old analog circuits. People use sort of fuzzy language, like there's warmth, imprecision, drift, character. That's true. Like, that's what I love about my stable of analog synths. They have all of that. But then the interface is really important. So Steve showed us a picture of the DX7 that had one data knob on it and a bunch of buttons, and a lot of obviously it was cheaper to make synths with fewer surface controls, because those were all parts that costed money and someone needed to solder them. So there was a move after these amazing synths with these expansive knob per function control surfaces. After this, everything went down to like a single, some buttons and a single data slider, as some of you maybe remember. I just wanted to talk about kind of the different types of programmable synths. So this kind of gets into splitting hairs, but conceptually, I think it's important, especially if you're really interested in them. There's kind of 3 or 4 different types. They kind of come in different flavors, these programmable analog synthesizers. So the first ones are the originals. They have fully analog audio and modulation paths. So that means that the the oscillators, filters, and VCAs, they're all made out of discrete analog circuits. And then the LFOs and the envelope generators, they were also discrete analog circuits. The crazy thing about these two synths, in my mind, I don't know if anyone's ever serviced them, they have discrete digital voice assignment. These things did not contain microcomputers. So when you played that keyboard, all those gates went into a whole bunch of electronic digital circuitry, which then figured out which voice to trigger and which control voltage to send to which voice. I'm going to show you a couple of examples of that. Then the revolution came when you had fully analog audio and modulation paths, but then you have a microprocessor with software that does the voice assignment and handles patch memory. These two synths had limited patch memory. You could memorize some of the settings, but not all of them. These were fully programmable. Every single parameter could be memorized by the computer. Then, sort of to cut costs and to make things a little easier, you started to get fully analog audio paths, but then things like the envelopes and the LFOs were generated by software. And that's kind of interesting because the Roland Jupiter 6 example, sequential circuits property 600 as an example. The interesting thing about these ones is they both use these very rudimentary processors. So the software generation of the LFOs and the envelopes were quite rudimentary. They were steppy. And then you get into what I call precision oscillators, which are digitally controlled oscillators, and then later on you get into direct digital synthesis. But they have an analog VCF and a VCA, and then they have a digital modulation path. These are now, so the Roland Juno 106 is an example that had a digitally controlled oscillator. That's where you use the computer to control the pitch of the oscillator, but the oscillator is still generating an analog ramp waveform, which then goes to wave shapers to generate your triangle and your square. And then sort of starting in the analog renaissance, started maybe around 10, 15 years ago, you started to get more synths that there was a marketing about saying this synth has a pure analog signal path. You have analog oscillators, analog filter, analog VCA, and then they kind of wouldn't mention that all the modulation sources were digital because for some purists that they didn't like that. This is an example. This is the Oberheim 4 voice. This had 4 discrete synthesizer modules in it. Some versions of it came with a programmer that allowed you to select some of the parameters. This is the one where the voice assignments were done through discrete digital circuitry. I serviced one of these once, and I did not want to touch the digital boards. It was like a 6-board sandwich. It was just bananas. This is the very first fully programmable polyphonic synthesizer. This is Dave Smith's sequential circuits Papa 5. And he really took a cue from the Minimoog. That was a very popular synth at the time. He basically just took something that kind of looked like the Minimoog panel and made it polyphonic. And then my personal favorite, the Roland Jupiter 8. This was their Roland's flagship 8-voice polyphonic synthesizer. I'm going to come back to this a little bit because this is sort of my favorite synth and kind of my reference design that I like to refer to. And then the reason why I wanted to share all this esoteric knowledge with you people is that there has been this massive analog revival that started with analog monosynths about 15 years ago. And over the last decade or so, there's just been a slew of analog polysynths. These are all brand new, currently available synthesizers you can buy. So the Udo Super 8, which is kind of modeled on the Roland archetype. The Moog just released the Muse a few years ago. Korg released the Prologue. And then Behringer is now rampantly just going through all the old popular synthesizers and making their own versions of them. And so this is their version of the Oberheim OB8. And what I find interesting is that these are all polyphonic synthesizers. They have analog signal paths. Some of them, I don't know all the details of each of them. Some of them may have analog modulation paths. I don't know. But what I'm fascinated about is how do they achieve this using modern technology, because what I'm going to go into is how did they do this with these synths from 40, 45 years ago, and talk about some of the limits and difficulties in designing these synths, and how you can achieve that with modern components and techniques. So designing a programmable analog synthesizer, what do you need to do? So first you have to design, well, first you have to do all of this. You have to design the digital control system. So you have to read your potentiometers using an analog to digital converter. You typically multiplex this, so you have multiple potentiometers that are read sequentially, so you can use a single analog to digital converter to read multiple potentiometers. You need to generate all your control voltages, and we're going to get into how many bazillions of control voltages you need to generate in real time to control an analog polysynth. Typically, digital analog converters can be expensive, especially high-resolution ones, so that would also be multiplexed. You need to be able to read all your switches. You have to control all the blinky lights on your control panel. You want to have MIDI control. So that's the digital side of things. And then you have to design all of your analog voice systems, and they all have to be voltage controllable. So if you're working with a synth that has an analog signal path, audio signal path, then you would have to have analog VCOs, VCF, VCA. Then if you're a Puritan, you would say, well, I can't have software generated envelopes or LFOs. They need to be voltage controlled analog modules as well. And then what I'm going to talk about most is designing the modulation control, because this creates an interesting and difficult problem when you're designing a programmable synthesizer. And that's designing low offset VCAs that control control your modulation sources. I'm going to get into what that means in a minute. And then, of course, you have to write all the software that ties everything together. It's a big undertaking. So this is kind of the general outline of how programmability is achieved. So remember, I showed you early on. This is these are your repeated synth voices. So I showed you the archetype of two oscillators going into a mixer, going into a filter, going into a VCA, and then depending on whether or not you're having software-generated envelopes or not, you might have a couple of envelope generators. These are typically, on the old synths, these were separated into individual voice cards, right? So this is the analog section of the synthesizer. You need to read all of the potentiometers. They go through a multiplexer. They're read by the analog to digital converter. So all of that control information goes into the CPU. It interprets what's happening here. It generates all your control voltages, and then it will that will go through a multiplexer to generate all of the voltages that you need to control all of these synth voices. So this red arrow this could be 32 channels of CV, or even more, depending on the synthesizer and the number of voices and how much modulation you're controlling. In addition to that, you need to read the keyboard, you need to read all the switches, and that also needs to go to the CPU. I'm not going to go, the switch latches, that's sort of, you get into control of analog switches. I'm actually not going to talk about that today. And so this is where you get into the details of how do you control the modulation of a synth voice, right? So Tristan talked about how you can take, in modular, you can take any modulation source and you can patch it into a filter or an oscillator. You control the pitch of the oscillator, you control the cutoff of the filter, the resonance of the filter. In a programmable synth, Tristan gave the example where you have a knob, and so this is how you do it in a conventional control. You'd say, I want to modulate my VCF with an envelope generator. So your envelope generator would get patched in, there would be an attenuator, and this knob just works as a voltage divider, and so when it's turned to 0, then you have no matter what the envelope's doing, no matter what voltage is coming out of the envelope, it's not going to modulate your filter. Maybe you want to do something fun, like you want to frequency modulate at audio rates. You want to frequency modulate notice these knobs go up to 11. I've just noticed that. So you would you turn this knob up. It's just acting as an attenuator voltage divider, right? If you want to add computer control to this, you then need to separate this potentiometer from the voltage that's controlling it. And the way that you do that is with voltage controlled amplifiers. So this is how you get programmable modulation control. So if you want to modulate your filter with your envelope generator, then what you need to do is you need to put in between the output of your envelope generator and the input of your filter, you need to put a VCA, and then that VCA needs to be controlled by what we call the envelope amount CV. This is just how they're referred to in the block diagrams and service manuals of these polyphonic synthesizers. This voltage is generated from the DAC. It's determined by this knob, which would be read by an ADC, right? So this is the abstraction of separating the potentiometer from the direct control of the modulation amount. So you have to use a VCA here. So in the case of a polyphonic synthesizer, you start to multiply VCAs, like you start to have dozens and dozens of these VCAs in a polyphonic synthesizer, and they need to have some specific properties to work well. And that's what I'm going to talk about. So I'm busy emphasizing the VCA, and I put a red circle on it to remind me this is what we're going to talk about next, is how do you design these VCAs so that they work and achieve programmability. And just to clarify, like, the reason why this is programmable is, I kind of maybe didn't hammer home this point, but this allows what we call patch recall, right? So if you set a knob to a certain amount, you can store the patch. The value of this control voltage is stored in memory, and then every time you go to that patch, the amount that the envelope is modulating the filter is determined. You can then change that amount, save it to another patch, and this voltage will be different when you go to the next patch. Anthony.
So I've noticed that some, very few synths have motorized potentiometers as part of the recall. Could you maybe explain where that would fit in? Because, like, we all dream of motorized everything.
Yes.
You know,
Yeah.
Can you maybe talk about where that comes into play in this?
That is, there's a whole design philosophy around that, and people argue about it on the internet, which may surprise you. So if you go back to, if you don't mind, if you go back to something like this, right? These are not motorized knobs, right? So those are your buttons that you use to select your patch, right? So you could change all these knobs, create a sound that you really like, store it in patch memory, patch number 32, and then you could then change all of the knobs and store it in patch 31. But if you go back to 32, then the knob positions do not match the tick marks, right? So you don't know. And so there was Dave Smith, who made this synth. He thought long and hard about how to do this. I don't think anyone ever really agreed on how when you turn a knob you're modifying a saved patch, how do you pick up that, like, do you jump to the new value? Do you have to sweep through the stored value? Do you put a ring of LEDs around it so you know where you are relative to the patch? Do you use encoders rather than potentiometers? I'm old school. I prefer not motorized faders. I'm happy to grab a knob and not know where, and be blind and not know where its memory setting is, and just grab it until it changes. But there's an Australian company, I believe, that makes a synth that uses motorized, not motorized faders, but motorized rotary potentiometers. And it's pretty freaky to watch, right? Because I guess you guys are all engineers, you're used to motorized faders, right? But I'm a synth guy, I'm not used to that. So it's sort of frightening to see all these knobs all moving at the same time. They were very expensive, and they all had to get them custom made, and of course they ran into service issues.
What was unique about Dave Smith's approach? Sorry, I don't know if I...
Oh, yeah, okay, so to go back to that, Dave Smith, so I need like let's use this example here. So here's a knob that's set to 4, right? And so if you store that in memory, then that's where it would be, right? If you went to another patch where this was in memory was set to 0, right? Then if you were to, that knob is sitting at 4, right? But if you don't touch that knob, then the setting is being pulled from memory and it's 0, right? So then the design philosophy is, well, what happens when you start to adjust that knob at position 4? Because your analog to digital converter is going to read 4, and then your CPU is going to say it's 4, but it knows that was previously 0. So the early synths, they would just, as soon as you started to move that knob, your CPU would detect a change and it would jump to that new value, right? So that would mean if you had no modulation, you would jump up to 4 right away, right?
Yeah, not good at performance.
Yeah, exactly. But the idea is that with programmability, you may only have your modulation wheel that you're using for your performance aspect. You're playing your keyboard. For one song, you have one patch. For another song, you just go to the other patch. You wouldn't touch any of the other knobs, right? But people really thought long and hard about this. That's why Dave Smith, ultimately, when he started making analog synths again, he's moved to encoders, because encoders were all relative, right? You could just start up you could start wherever you wanted, and he had different settings with it. This was the Prophet 08, released back in 2007. He had different settings, and the funny thing is that the analog synth guys that wanted these big expansive interfaces, they hated the encoders, and Dave Smith Instruments was forced to release a new set of control boards that had real potentiometers on them. People were so mad about these encoders. They're like, I want a real analog synth that's got the potentiometers have stops. They stop at 0 and they stop at 10. And so I remember getting one, and I bought the pot kit. I replaced all my encoders with potentiometers because I did not like those encoders. Because in my mind, this problem that you're talking about, I don't care about it. I'm like, I like the jumping, right? But some people would say you have to turn it down to 0 and pick up the new value, and then you go from there. But we're getting ahead of ourselves.
That's why we're here.
That's right. Yeah. So we can. I haven't even really got into the weeds yet. So I'm glad you're so detail oriented. So this is where we're going to get into the weeds. Hopefully not too deep in the weeds. Yes. So hold on. I gotta go back here. So we're going to talk about how they, the engineers of late 70s and early 80s, how did they design these VCAs? Because these VCAs, compared to modern VCAs that are available, they had some non-ideal behavior that we're going to talk about. So vintage polysynths, they used operational transconductive amplifier-based VCAs. Some of you have probably heard of the CA3080. If you're a Roland nerd, you'll know about the BA662. And then the only one that's still in production, in full sort of major production, is the LM13700. Not actually used in any polyphonic synths in the late 70s or early 80s, as far as I remember. Some of you are probably familiar with the operational amplifier, right? So the OTA it works like an operational amplifier. It's got differential inputs. It's got a non-inverting and inverting input. Typically would take a bipolar supply. But what makes it different from a conventional op-amp is that it has a current-controlled gain cell, and it has a current output. And so this is the what we call the gain cell that was used to make all of these VCAs that control the modulation depth in these polyphonic synthesizers back in the day. If you really want to learn about the operational transconductance amplifiers and you want to know about everything that's wrong with them and all the ways in which you can try to make it better, but it's probably not worthwhile, you should read this paper by this guy. His name's Matt. If anyone's on the Modwiggler forums, he's known as Guest. That's his username. I think, if you do some digging, I think he's actually like an engineering prof in Chicago or something, but I might get in trouble for I've had a bit of correspondence with him. He wrote an entire self-published paper. His website's Open Music Labs. He talks about minimizing distortion in operational transconductance amplifiers because from a audio perspective, they have a lot of distortion. For control voltages, you don't worry as much about that. This is an incredibly amazing and deep paper if you're interested. It's just available. You just download it from his website. But what I want to talk about are the non-ideal characteristics of OTAs. To refresh your memory, these are what make up the VCAs that add all this wonderful programmability to an analog polysynth. So this is a 3080. The conventions are a little confusing because this symbol is meant to indicate a current mirror. That's actually where the control current goes in that controls the gain of the OTA. In this example that I pulled off the internet, they've just drawn it as a separate line here. Well, what I want to show you is you have the inverting input, the non-inverting input. You would typically apply the voltage. Imagine this is the voltage. This is an envelope going in, for example. So V in would be something like your envelope or your LFO. V out would then be going to your filter or your oscillator, and your in this case this is grounded, but you would be applying a voltage here, which gets converted to a current, and then you're applying this control current to the control current pin, which controls the gain of your VCA. And the issue is in this non-ideal behavior is that, like conventional operational amplifiers, you have input offset. And so what that means is if you have 0 volts, if you have your inverting input grounded, and let's say that you apply 0 volts ground to your non-inverting input, the output should be 0, but it will actually be some tiny amount. Back in the old days, it would be like several millivolts. Now you can get things that are in like the nanovolt range. They have almost no offset. And so I'll explain why that's an issue in a minute, because we're talking about millivolts, right? And you think, well, a few millivolts, like if you think of audio, like a few millivolts is not really that big a deal, right? But when it comes to controlling the pitch of an oscillator, it becomes a problem. And then the other thing I'm going to talk about, which is related to this, is that this is not a fixed offset. It's not like this OTA just has 3 millivolts of offset all day for its whole life at every temperature. That you could deal with. The problem is that the offset voltage is a function of the control current. I'm going to get to that in a second.
I'm
Yes.
trying to give you negative feedback, but I have to say that negative feedback is how audio works.
Yes.
But in this case, I don't see negative feedback.
Yes,
Could
yes.
you maybe explain that?
Yeah. So OTAs are kind of cool that way. They typically, in this configuration, they don't use any feedback because you have the gain is controlled by the current, right? So if there's no current flowing into the control pin, then the gain is 0.
So have we been calling them VCAs when they're really current-controlled amplifiers?
Probably yes, because we are. Yes, because we are. I don't know about some of the. So you audio engineers probably know about the VAT, THAT, VCAs. I don't know much about them, the Blackwell cells and all that stuff, but I have a feeling they might be current controlled as well. You just have to convert that
We're
voltage
all
to
wrong.
current. Maybe.
I appreciate it.
Yeah. Okay, so now I'm going to get into why do we care about how well designed these VCAs are and about this offset current, right? So this offset voltage that appears on the output. So when you're designing a VCA that's controlling the pitch of an oscillator, you have a problem of control voltage feed through. And so I'll get to that in a second. It's related to the fact that the offset changes with the amount of control current. So imagine you are playing your synthesizer and you have an ADSR envelope and you have, it's going into the VCA. The amount the envelope is modulating the VCO is determined by this control voltage, right? And so what I showed you before is the amount of this control voltage. If this control voltage is 0 versus, let's say, a typical control voltage range in one of these old synths would be 0 and up to a maximum of 10 volts, right? So maximum amount of the envelope would come through when this CD is 10 volts, and there would be no envelope coming through when it's 0 volts. And so that's fine, but imagine you set your synth into a drone, right? You open your VCA and you're just listening to your oscillator's drone, and your envelope is not triggered. It's not being triggered. You're just listening to this nice Brian Eno like drone on your synth, which I do a lot. Then if you grab your knob or your slider and you increase the amount of the modulation depth of your ADSR, ADSR is not triggered. It's just putting out 0 volts. But if you increase this CV, then you change the offset on the output of this VCA by a few millivolts. And the problem is, as Tristan was talking about, we have this analog oscillators typically work at this 1 volt per octave standard. That's 0.833 millivolts per cent, right? A cent is 100th of a semitone. And so if you have something like a 5 millivolt offset, which doesn't seem in theory like a lot, that will, as you move this slider, your oscillator is going to go out of tune plus or minus by up to 6 cents, right? Which some people can hear that, and from an engineering perspective, it bothers people, right? So you want to be able to adjust all of your sliders without your VCOs going out of tune. So you need to do something about this voltage, this control voltage, it's called control voltage feed through, which is related to the fact, which is basically another way of saying that this current pin, the current amount affects the offset on the output. So ditto for your LFO, right? So this is a problem. How did they fix it back in 1980? This is an example of an OTA-based VCA in the Roland Jupiter 8. And so they trim the offset voltage. So this is a BA662, which is an OTA cell. So there's your current control input that controls the gain of the VCA. You would have your modulation source, your VIN. The thing I didn't really talk about is that these old OTAs, they could only handle voltages inputs in the millivolt range. So you'll see there's this massive voltage divider that would divide a signal that would typically be 0 to 10 volts. It's getting divided down to just less than 50 millivolts. And then what they would do is, and then here's your control voltage comes in, gets converted to a current, and that is applied to the control pin. And then what they would do is to minimize the offset in the output, so they would add a bias voltage to the, let's say this is the non-inverting pin, they would add a bias voltage to the inverting pin, and so your bias would then, you would adjust this trimmer, and you would bias it, you adjust it so that the bias voltage that appears on the inverting pin is equal to the offset voltage that's just innate to the OTA. And so then the idea is that it gets canceled out at the end, and you don't have a problem with this offset. But if you've been paying attention, you'll know that this offset is not fixed. It changes with this control voltage. And so what they had to do back in 1980 is these OTAs, they came out of the factory, they had different, they had a wide variety of control voltage feed-throughs and offsets, and they would hand select them. So I don't know if anyone serviced voltage Roland synths, but the BA662s, they were bins. So someone would, they put them in a jig, and they would measure the offset, and then they would put a little dot of paint on it, and there were red dots, and there were orange dots and white dots. And so in certain applications, you could use ones that had, so there's, by the natural processes, random processes of manufacturing them, some of these would have very low control voltage feed-throughs, maybe only 2 millivolts. So 2 millivolts is less than 3 cents, so they would be like, that's fine, we don't really care, we'll just use that. But they were hand-selected back then. And because, oh yeah, sorry, I'm going to get to this in a second. I'm going to come back to this idea of this voltage, this trimming and control voltage feed-through. The issue with this is a trimmer. You got to, so some technician in the factory has to hand adjust this. So this is the schematic for a single voice card in a Jupiter 8. And there's a whole bunch of trimmers for tuning the oscillators and scaling the filters and everything. So there's already like a bunch of trimmers I haven't even highlighted. But I've highlighted 5 what they call balance trimmers. These are the trimmers that are trimming the modulation controlling VCAs. This single voice card has 5 of them. The Jupiter 8 has 5 of these voice cards. So all of a sudden when you make this synth, just for the modulation depth control, you have 40 trimmers that need to be adjusted. This is what they did back in 1980. So this is like back in then, they would do that. Nowadays, all these in the new wave of analog polysynths, I don't think they do that anymore. And so I want to talk about maybe what some of the solutions are. Just to hammer home the point, this control voltage feed through that I'm talking about, which is control current dependent offset, that's another way of putting it. This is kind of what it looks like. So if you have your control voltage going into your VCA at 0 volts, you could adjust that trimmer and you could adjust it so that you have no offset. But as you increase your control voltage, you're going to hit some maximum usually, but not always. It's around the center point of the range of your control voltage. And then you get to your maximum control voltage, and it drops back down to 0. And this offset can be anywhere in the range of 2 to more than 10 millivolts, depending on how the parts were binned back in the day. So you would hand select anything that was controlling pitch. You would have to hand select something that had a control voltage feed through of no more than 2 millivolts. For other things like were more audio related and not pitch sensitive, you could use something that maybe didn't have as good performance. What do we do now? This is the #1 way that we fix this problem. So what are the modern solutions to the problem of these VCA offsets? The way that they do it now is they use software modulation, and that's actually what they did after that first generation of synths like the Jupiter 8 and the Prophet 5. They just, as much as they could, as the processors would allow, they started to digitize all of the modulation sources like the envelopes and the LFOs. Just for contrast, this is how they originally did it. So you would have a voltage-controlled envelope generator that had, if it had 4 stages, you need to generate 4 different voltages for each stage. If your voice had 2 envelopes on it, which was pretty common back on the flagship synths of the day, then you would have 8 control voltages just to control the 2 envelopes per voice card. So that would mean if you had 8 voices, then you're already at what? So that's 64 channels of DAC just to control the envelopes. So you can imagine that back in the 80s, as soon as the processors got good enough to generate envelopes with software, they quickly abandoned the analog modulation sources, and they went to just generating this pattern, as Tristan showed us, because he literally wrote, that was a digital ADSR you showed us that you made, right? They would write the software that would generate the change in voltage over time. That would go to a DAC, that would generate a control voltage, and that would be applied to the VCO. That would just be summed with all of the other information that's controlling the pitch of the VCO. You don't have to worry about this problem of offset. That's what everybody does, I think, now. So for example, Dave Smith, when they re-released the Prophet 5, it almost certainly has digital envelopes and digital LFOs, whereas the original late 1970s version used analog modulation sources. Some people will complain about that. They'll say it's not woolly enough or it's not original enough. So that's what most people do now. The other solution is to just use a better VCA, because there are much better VCAs available than these OTAs from the 1970s. One example is the 2164, which some of you may encounter because it is I think it's somehow descended from the Blackwell cell. So what's the VAT VCA that everybody loves? 2180? I can't remember. Anyway, this is a very good VCA. It has low control feed through. So you literally eliminate this when you apply the full range of control voltage to this. the offset doesn't change, or it barely changes, or it doesn't change in any musically noticeable way. The problem with it from a design perspective is that it's pre-configured to have an exponential response. In an analog polyphonic synth, you typically want VCAs that have a linear response. So what that means, so there are examples of this. So has anyone heard of Black Corporation? There's a few nods. So it's a Japanese anyway, it's complicated because the guy that runs it, Roman Filipov, he runs it out of Japan, but he lives in California, but he's originally from Russia or something like that. He's opened he makes a bunch of polyphonic synthesizers that are rack mount units. He's opened his schematics, and you can build his synths. They're available as DIY. His synths have dozens and dozens of these 2164s, but at the input to every control input, he has a linearizing circuit that takes your linear, exponentiates it, because you need to get a linear response out of this VCA when it naturally has an exponential response. So, and these are quite expensive, because these are really meant for audio, right? So it seems sort of like from a design and economics perspectives, it seems like kind of a waste to use this premium audio VCA just to control the modulation depth of a slow-moving signal like an envelope generator. This has just come out. This is Dave Rossum's company, SSI. They just released something called 2190. It's a hex mixer, so you don't have the individual outputs. It's so new, they haven't even defined their control voltage feed-through. You see it's XXdB. Another potential solution, except that it actually sums all the outputs, so it's maybe not totally appropriate. Lastly, this is what I did. And this was fun and silly, and we probably won't do it, but what we wound up doing was we did digital offset trimming. So here's my modulation source, and it is going into the modulation depth control VCA. It's controlled by the amount of modulation that's going into the VCO, is controlled by the mod amount CV. And what we actually did was we took our microcontroller, and I think of microcontrollers, STEM32s, things like that. They have what I call a free DAC on them, and they have a free ADC because you buy the microcontroller. It's got a 12-bit DAC, and it's usually got a 12-bit ADC on it. These are good enough for generating the offset voltages that you need. So we take an original OTA with all the non-ideal behavior and voltage-dependent offset, in CV-dependent offset, CV feed-through, and we literally apply the CV. We go from 0 to 10, and we measure the output offset, and then we apply the reverse of it, the mirror image of it, to the inverting input. And then what this achieves is that once you do this, you now have I gotta get this sentence out. You have a CV-dependent offset generation. So you're trimming this in real time. This offset voltage is changing based on the amount of CV. We did this, and so the idea is that when you're building a modern synth, you build it in the factory, you just want to run a calibration routine. You don't want to have a technician sit and do a whole bunch of trimming, right? This achieves, you get to use the original VCAs with all their woolliness and the fact that they're available and inexpensive. It's a lot of routing on the circuit board, but it's not actually a lot of external components. So we got it working, and we're kind of happy with it, but we will probably abandon this and probably just use a better VCA.
Rule 2.
Yeah. That's all I wanted to talk about. If anyone wants to know a little bit more about some of the building blocks, I have a few more slides, but we're probably out of time. I'm System 80. There's some sound demos of our modules on SoundCloud. There's my old internet handle. And our designs are mostly open source, so if you want to go and look at the KiCad files, and the software that we write to control our modules, that's all on GitHub, very poorly documented.
We're approaching the end of the night here, and I hope that ramped up. Some people stuck around, specifically for this stuff, and some people got more attention because of the detail that we go into. So I appreciate that, Jeff. I kind of have 3 questions for the 3. I've kind of been thinking about them all night. So, like, Steve, why is Behringer and Uli such an important person in the synthesizer industry? And maybe, like, I don't know if you know about Cool Audio. You probably do. Do you know about Cool Audio? Okay, so maybe talk a little bit about that, and then you jump in on the Cool Audio part.
I
about
sure
it.
will.
Like, why are they so important right now?
So Behringer is a really polarizing figure personally and company. And what he has done is he has built a business model on taking advantage of designs that are now no longer protected by patents. So he started out making clones of Mackie mixers, and they were a little cheaper, but they did pretty much the same thing. And then he started doing it with synthesizers. And I don't know all the details. You probably know more about it. He outsources everything to offshores everything, uses cheaper parts, cheaper labor, and can produce decent clones of these synthesizers that everyone wants at a fraction of the cost of the original manufacturers, and it's legal
In China.
and some people say, well, there's no other way I can afford this, and as a musician, it's important that I have it, and it's tough to argue with it.
Yeah. So maybe talk about Cool Audio. Like, why is Uli's little side hustle so important?
So we talked. What I didn't get into, which is sort of some other slides, when these synths, they use all these vintage synths, these polysynths. They took all the discrete oscillators, filters, and VCAs, and they eventually compressed them into their own individual ICs, right? So they integrated them. So instead of having a discrete VCO with a bunch of transistors and capacitors and op amps, you literally just have a little chip that just is a VCO. You have another chip that's a filter. They even started making them that were just an entire synth voice on one chip. So you had a VCA, VCF, VCO. And in order to make clones of some of these synths, you can't really authentically make them unless you use these out-of-production chips. And so Uli, as Cool Audio, I think he bought Cool Audio. Cool Audio just existed before, and he said to them, you now clone the Roland BA662. Bucket Brigade delays were a big one. So he was like, no one's making Bucket Brigade delays, so Cool Audio is like, you now make Bucket Brigade delays. You now make 2164s, the VCA. And so he has all these chips made for his synths, but then he also sells them. So I'm working on a design with a collaborator that uses some Cool Audio BBDs, right? There's another company in Latvia called Alpha, and they do the same thing. They have some old Soviet era foundry, and they have the process where they can make all of these old chips. And so that's part of this analog synth revival, is that you could make great synths without using these original chips, but there is this idea of authenticity, that it's not the real thing unless it uses the original chip. So Uli and a couple of other companies have gone to the extent of actually making the chips.
So do you have a home lithography plan? I'm
No.
You got a foundry at home? Okay. I think it's a very important company in the synth world.
Yeah.
And I think it's one of those kind of industry secrets that nobody really knows, that like how important the role it actually plays.
Yeah. So for me, like, Behringer is a double-edged sword, because they make modules that are quite a lot like my modules, but they make them for like a third the price or less, and they operate on much. They brag. I mean, he's very open up a business plan, right? So if you follow the Behringer Facebook group, they're always bragging about how they were protecting the little guy, and we're not greedy, and we're operating on the thinnest of. and that's why we outsource everything. That's why we moved our headquarters to Malaysia, because we don't want to pay taxes in Western Europe. I'd say they're antagonizing because probably lots of other companies do this. They just don't tell you. But Behringer's like, this is how we make it so cheap for you.
To throw some numbers out there, I glanced at Long McQuaid's website yesterday. Looked at the synthesizer section, and there was like 300 or 400 synthesizer devices I could buy from Long McQuaid. I looked at the Eurorack modules, and Behringer popped up. There's other modules, $2, $3, $4, $500. There's Behringer, $49.99.
Yeah.
How can you beat that?
Okay, yeah. So democratization, that's kind of a double-edged sword. You said it very well. Okay, so this is kind of a Tristan question, and maybe you all can jump. Okay, so I've heard one time that things sound best right before they're about to explode. So what is it about analog and distortion and pushing things to the like magical edge that gives these technologies the buzzword? Insert buzzword here.
I did have a couple slides about digital versus analog that I cut out just for time restraints, but the thing about analog is the nonlinearity, it's the distortions, the non-consistency, the temperature changes, the real-world variations of just humidity can modify a circuit if it's not designed to ignore it. And that allows, like, as you push the analog realm, you reach that range of, it's not supposed to operate like this. It's not designed to operate like this. Nobody really knows what it's going to do. You can predict it, you can measure it, but you design a circuit to operate within this range. When you push the signal past it, it's not designed to do that. What is it? What's going to happen? That's what makes things sound unique and interesting, and give characteristics that we love in music and sound creation. Is that unknown, that non-linear, that distortion and stuff.
Steve, you want to maybe add to that?
Yeah, I was thinking about this a lot when I was putting this presentation together. Is there one thing that I could say about, why are we drawn to analog synthesis? And it seems to me, I mean, all of what Tristan said is absolutely correct and inarguable. And I've been thinking a lot about filters because I love filters. And we had in the 80s and 90s, we were trying to get the perfect sampler because we thought samplers would change the world and solve all our problems. And of course, the original ones sounded terrible. But the ones that we get nostalgic about are like 12 and 13-bit samplers with analog filters.
Yeah.
And the analog filters, it's like why do I like mastering something with an ATR 102 plugin?
Yeah.
Why do I feel that sounds better? Why do I like overdriving a filter? Why does an EPS sampler sound better with the filters infused?
Okay.
I don't have answers to any of those, but these are the thoughts that keep me up at night.
So I went back to this slide because just when you talk about warmth and imprecision, the actual like definable example here with this Oberheim 4 voice, 1, 2, 3, 4 identical synth modules, right? And you dial in so you have a control panel that dials in like the filter cutoff and the resonance amount and something like that. But when you program this thing, you have to hand set all of the envelope generators to the exact same amount. If you want to play, so when you press one note on the keyboard, you press it. If you press it again, you press it, voice 1 plays. You press it again, voice 2 plays. Voice 3, voice 4. Cycles through the 4 voices. If you're just pressing one key over and over again. If you listen to this synth, because I had one for repair years ago. Every time you press that key, it's not exactly the same because you can't dial in the voice just the same. And even if you go to something like a Roland Juno 106, which has digitally controlled oscillators, very tightly controlled pitch, the way the filters are calibrated and the way they resonate, each voice is slightly different. So again, if you start cycling through those voices, each analog voice is different. All these modern analog polys will not do that because they are, like, even to my point about, like, oh, look, we've done digital trimming to perfectly calibrate our VCAs. On an old vintage synth, all those VCAs are trimmed, then they all drift, and so then even at the modulation depth amount, you've got offsets contributing. Each offset is a little bit different for each voice. That's not like about distortion or warmth, or that's just about the actual limits and behavior of the system.
So then, like I ask Steve, you start here. You know, like, is the magic in the randomness, or is the magic in the precision, or is the music come from the noise? Like, where does the magic exist in these things, and how do you get it out?
Well, we crave change, you know? It's like you can create unlimited polyphony with a divide down organ model, but then because that exists, we need to introduce a bucket brigade chorus device because we just don't like hearing something that's exactly the same and consistent. And I think not the downfall, but what was disappointing about sampling, it's like the Fairlight sampled one of the most amazing moments in music, the orc hit from Stravinsky's Firebird Symphony. And you've heard it a million times, and you don't care, and it sounds terrible, because every time you hear it, everything's exactly the same. The phase relationships are the same. I mean, it was a terrible sampling rate and bit depth to start with. But I was in the York Music Labs as a student, and I had the system on 100M, and I put together this great patch. I think I'm going to sample this thing and use it all the time. And the second time you play that sample, it's almost like an uncanny valley thing. Your brain goes, well, I just heard that. I don't need to hear that again. So that's, again, my layperson's guess.
No, that's very good. That's very good. Well, folks, you know, let's give our presenters a round of applause. I really want to thank Since When for showing up and helping us. So if you got broken synths, Since When. Gare Audio, Sono Technique, avshop.ca, Adamson Audio, another great Toronto company, Lawo, Solotech, Toronto Metropolitan University, as well as the University of Toronto here.